Now, this might seem more like a biology lecture at first, but bear with me, folks. Now, if you've ever spent any time at a lake or a pond over the summer, you probably saw an insect known as a water strider that can literally walk on water. Have any of you ever thought about how they can do that?
I guess I always just thought it was because they're so light. I mean, they don't weigh very much, so they can kind of float on the water.
Well, it's certainly true that a much larger animal like a mouse would not be able to accomplish this, but a small mass is only part of the explanation. For example, if you carefully place a coin on the surface of water, it will remain there without sinking. However, we know that coins are too heavy to float because they have a greater density than water, so there must be some other mechanism at work.
I guess they aren't actually floating now that I think about it. Something that floats is often partially submerged, but water striders and those coins you mentioned actually rest on the surface.
Right. And they rest there because of... anyone? Because of something called surface tension. That's what I want to talk about today. Now, in simple terms, we can think of surface tension as something that allows the surface of a liquid to behave as a kind of film or elastic sheet. Surface tension refers to the forming of this film when a liquid is exposed to a gas. So, if we picture a glass of water, what do we know about the water?
It is composed of hydrogen and oxygen molecules.
Yes, good. And these molecules are essentially bonded together through what is known as cohesion. Does anyone remember what cohesion is?
The water molecules exert attractive forces on neighboring molecules.
Exactly. So, if we looked at water molecules, let's say 3 inches below the surface, what would we observe?
We'd see those water molecules exerting attractive forces on all of the other water molecules surrounding them, and there would be molecules above, below, and on the sides of every molecule.
Excellent. Now, keeping that in mind, what would be different if we examined the water at the surface?
Most of the water molecules would have other molecules to the left, right, and below, but none above.
So, the cohesive forces holding those molecules together would be stronger or weaker?
Stronger, because there are fewer surrounding molecules to spread this force to. You've got a certain amount of force being split up by in 3 directions, not 4 like you'd have if there was water on top too.
Yes. Does everybody see what we're getting at here? Surface tension is the result of greater cohesive forces between surface molecules, which is what allows insects such as water striders to walk on water, or objects like needles, which would usually sink, to rest on the surface. Now, one last thing. As you can probably guess from this lecture, is that the surface tension of water is not usually extremely great. Otherwise, much larger objects would be capable of resting on the surface of water. Let's say you, very carefully, got one of those coins to rest on the surface, and then you just swirled your finger around a little bit to disturb the water. Down goes the coin. You have essentially removed the surface tension by disrupting the attractive forces that created it, which is why any insects you see walking on water will be in a calm pool. They can't do it in a turbulent stream. These attractive forces are also responsible for the formation of drops from a dripping faucet, or of water beads on plants when it rains. In physics, surface tension is a mathematical value which can be calculated using various formulas. So, next class, we will begin to use some of them to examine the effects of temperature and water additives on surface tension.